Hello?
Yes, can you see my screen now and can you hear me?
Hello? Can you hear me? Can you speak again?
Yes, can you hear me?
Yes, perfect.
Great. Can you see my screen?
Yes. Please start when you're
Okay, so
ready. Please start when
I'm
you're
ready. Okay, can we begin now?
Yes.
Great. Okay, hello everyone. The title of my work is Semantics-preserving transformation of context-free grammars into level 1 form. And the first part of the talk is going to be dedicated to the background. The second part will delve into the technical details. So the background is in domain-specific languages, and specifically those embedded in Java. When we embed a DSL in Java, we use a Fluent API, which means we compose sentences from the DSL as a sequence of method calls. And if our Fluent API is safe, then the DSL is designed in such a way that the types, they disallow invalid syntax. And effectively, if the DSL type checks, then it is correct. And the type checker acts as a compile time parser. This is great, but when a DSL gets sufficiently complex, the Fluent API becomes increasingly difficult to maintain and evolve. And it also slows down type checking, which slows down compilation and the IDE. So let's look at an example. EQL is entity query language. It's based on SQL and it's embedded in Java. EQL is a part of Trident Genesis, which is a Java technology for building information systems. So on the figure, you can see an EQL query that is used as a Fluent API, and the programmer doesn't have to use low-level SQL. Instead, they use EQL, which provides high-level abstraction over SQL. The EQL itself is then compiled into SQL and executed. Now, the advantage of having EQL embedded in Java is that it leverages all the advantages that Java gets. For example, autocompletion. EQL is also safe. It allows only valid syntax, and errors are reported as type errors. For example, here we see on the left, we have order by, followed by limit, but if we remove the order by clause, we get an error because an EQL limit can't be specified by itself. Now, with all these advantages, the cost of maintaining EQL is not small. This is just a part of the Fluent API. In total, there are nearly 100 interfaces. All of them are heavily parameterized, and this kind of code is quite difficult to analyze and maintain. So if it is difficult to maintain by hand, let's use a generator. Let's generate a DSL. To generate a DSL, we need to know what makes a DSL in Java. First, the Fluent API, as we saw already, it's the syntax of the language. Then we have a parser and an AST. So these two components, they provide a runtime representation of our DSL so that we can then take a parse tree, we can compile it into SQL and execute it. So all three components are essential, and all of them can be generated from a grammar. Now, to illustrate this, let's walk through a subset of EQL. Let's consider the simple grammar on the left, which begins with select. It also provides other constructs such as where, conditions, comparisons. For now, we'll ignore group by and order by, since they will only complicate things. So let's focus on select. Select as an entry point needs to have a static method, which we see on the right, and select is followed by where. So the natural thing is to specify the return type of select to be where. And on the bottom of the right side, you can see how we use this Fluent API. Next, how do we define where? Well, we look at the grammar rule, we see that where begins with a terminal where, and where is followed by condition. So we translate it directly into Java, we define method where, which returns condition. Now when we come to condition, condition is a rule with alternatives. It doesn't have a single body like where, instead it is one of many things. We'll consider right now only two of them, and condition and comparison. So at first sight it isn't clear how to define it. So let's first try to define one of the alternatives. Let's define comparison. Comparison has a rather simple body. It contains only 3 terminals, and that's how we define it. We begin with prop, with method prop, which returns a type, a helper interface that has the method EQ just to chain our sequence, and this EQ method returns another helper which has the last method prop and whose return type is not specified. We'll come back to that later. The interesting part here is we know that comparison begins with prop, and we know that condition is comparison. So what we want to be able to call prop on condition. Currently we can't do this since we haven't defined condition yet. So we know that condition is comparison. Now if we translate this into the object-oriented model, we'll get that condition extends comparison. And therefore grammar rules with alternatives are modeled with inheritance. Alternatively, a prop could be defined as a non-terminal with a simple body prop, and this is to show how inheritance also applies in other cases. Here, comparison is a production rule. It has a body, and the first symbol in the body is a non-terminal. So here we also apply inheritance so that we can invoke method prop on comparison. But what should we use as the return type of prop? Well, if we look at the grammar, prop is followed by EQ. So can we just specify EQ as the return type of prop? And the answer is no. Since if we introduce another grammar rule that wants to use prop, such as isNull, then we see that isNull extends prop, and prop returns EQ. But isNull doesn't have EQ. isNull has isNull followed, which follows prop. So something generic is needed here. And generic we get. We just make all our interfaces in the Fluent API generic, with one type variable, a, which represents a continuation. And we see how nicely we can reuse interface prop, both for comparison and both for isNull, just by specifying a different type parameter. So that's another principle of Fluent API design, that we use type variables to generalize. And we also see how nicely a grammar rule under this model translates into an interface definition. They are almost the same. Now, coming back to AND condition. So we have defined comparison, we have almost defined condition, now we have AND condition. You see that condition and condition are recursive, since and condition begins with condition. So this is a case of left recursion. And it turns out that with this simple Fluent API design, we can support left recursion because it results in circular inheritance. That's one limitation. Another limitation is that we can't model first-first conflicts, also known as common prefix. Here, the grammar left, we have comparison, we have is null. Both of them begin with terminal prop. We also have condition, that is one of them. On the right, we have our Fluent API, where condition extends both interfaces. And the interesting part is that both interfaces have method prop with the same parameter list, but different return types. So we have condition inherit two prop methods that have different return types. And this is disallowed in Java. Consider what should happen if we call method prop on condition. Do we mean prop like in comparison or prop as in is null? The result is undefined. So we see that our simple strategy to Fluent API design supports only LL1 grammars. It doesn't permit left recursion, doesn't permit first-first conflicts, doesn't permit first-follow conflicts, which are described in more detail in the paper. So if we can apply our strategy, what other strategies can we apply? First, it was shown that Java generics are Turing complete, meaning that a Turing machine can be simulated in the Java's type system. In this work, it was shown that this method can be used to generate Fluent APIs for all context-free languages. So you could say that the problem was solved, but not really, since this method is not efficient in practice. It results in very complex types, and type checking becomes really slow. It was realized that something more practical was needed. Then came Fling. Fling is a Fluent API generator that supports all deterministic context-free languages, or equivalently LR1 parser. But in practice, Fling is limited to LL1, which makes it applicable to only the simplest of languages. So with this state of the art, we see that there is a lack of a tool that can generate efficient Fluent APIs and can support context-free languages. But we saw that our simple strategy results in simple Fluent APIs. So can we extend our strategy so it applies to context-free grammars and not only to LL1 grammars? That's the question. And the intuitive solution is to transform any given context-free grammar into LL1 and then use the transformed grammar to generate the Fluent API. Let's see how this turns out in practice. We take a grammar with left recursion and we eliminate left recursion via the most straightforward method. Then, using this LL1 grammar, we can generate a Fluent API using the method described previously. Then we can generate a parser. We can generate an AST even. But can we use the results of such a parser? And it turns out that probably not. On the left, you see the original grammar and you see the abstract syntax tree. They are almost equivalent. In fact, there is a direct correspondence, and this is the abstract syntax tree that we would like to use for compilation. Next, on the right, you see the transformed grammar and the transformed abstract syntax tree, which is confusing. It's not clear how to compile it. And from this, we see that transforming the grammar actually modifies the abstract syntax tree and the original semantics are lost. So by transforming a context-free grammar into LL1, we have succeeded in enabling simple generation of fluent API, but at the cost of losing the original semantics. So now if we want to combine both, the question becomes, how can we apply our transformation but preserve the original semantics? Which means preserve the original abstract syntax tree, so that we can use it for compiling our DSL. Now the core idea of the work is, first we take a grammar and represent it as a tree. For each tree node, we define two functions. One is the semantic function, another is the parsing function. Then when we transform the tree, we modify both the structure. When we rewrite the grammar, we modify the tree structure, and we also at the same time modify the functions. And the effect of this synchronous modification is that the resulting tree ultimately will call the original semantic functions, which means we will construct parse trees based on the original abstract syntax tree, thus preserving semantics. So let's walk through this by example. We see the familiar to us condition, comparison, and is null. We have the case of first-first conflict. Both begin with prop. So let's take this original grammar and its tree and define semantic and parsing functions. So here, by the way, in the tree, the dotted lines, the dashed lines represent alternatives. Since condition has two alternatives, is null and comparison. And blue arrows represent, they connect nodes that are a part of the same rule. For example, comparison goes to prop, and then prop is followed by a queue and by another prop, just as in the grammar rule. So coming to the functions, let's look at comparison. The semantic function for comparison is really simple. It calls the data type constructor, and it ignores the second parameter, EQ, since it doesn't have any meaning for the AST. So that's that. Then we have the parsing function, and note that it has a single parameter k. All parsing functions are written like this in continuation passing style, where k represents the continuation. So the result of parsing will be supplied to k. Now to parse comparison, we first parse prop and supply prop with another continuation, which gets access to the prop parsed. Then we parse the queue, then we parse the second prop, and then we call the semantic function and supply the result to k. So this is trivial parsing, but implemented in continuation passing style. The same principle applies to parsing is null. Now when we come to condition is a bit difficult because we have a common prefix. We know that LL1 parser cannot handle such conflicts, and we see it here where condition needs to select either comparison or is null, but it can't do so because it tries to pattern match where both cases match, and it selects different alternatives. So let's eliminate the common prefix. Now, after we have eliminated it, we have a transformed grammar on the right, where prop, the common prefix, has been extracted. And now we have this grammar and tree of different shape, and let's see how we can modify the parsing and semantic functions correspondingly. First, let's look at comparison. You'll notice that comparison now has one node less. It doesn't have the first prop. And the semantic function for this comparison prime doesn't have prop 1 either among its parameters. This means that it cannot directly and immediately construct comparison. It needs to delay its construction. And to do that, instead of returning comparison directly, it returns a function that will build comparison. This function expects prop 1 to be supplied later, and then it calls the original semantic function. This is the essence of this synchronous modification, that we retain the calls to original semantic functions. Now, the parsing function for comparison prime is implemented using the same principle as before. We parse EQ, which is first here, then we parse prop, which is second, and we call the semantic function for comparison prime and get its result, which is a function. The same is true for isNull. It also parses a function that expects prop to be supplied later and will build the original isNull. Now, condition double prime has two alternatives. It needs to select one, so it just pattern matches on the first terminal. Since we have an LL1 parser, it's called the first D1 token of lookahead. If it's a Q, it's comparison. If it's isNull, it's isNull. And finally, we come to the root of our tree. And this is interesting. Condition begins with prop, and then it has this condition double prime. Now we know that condition double prime will return a function, because comparison prime returns a function, and isNull prime also returns a function. So what we do then, we just apply that function to prop that was parsed first. And this is an interesting pattern that occurs when you eliminate a first-first conflict. It results in function application. Now I'll show how the semantic and parsing functions can be used to build a Fluent API and a parser. So looking at our transformed grammar, we build a Fluent API for it. Just like before, we make every interface generic. We parameterize where necessary. We use inheritance where necessary, and obtain the following. Now, that's just the Fluent API. How do we build a parser? For reference, we have the Fluent API. We'll just focus on comparison. And we have the AST. Please note that the AST is the original one, the comparison from the original grammar. So first, in our parser, we implement the interface and define the method. The minimal we can do, the minimum. Then we look at the parsing function. It has parameter k. So let's enhance our parser with a field k that will represent the continuation. Now the question is, what should this continuation accept as parameter? Well, the answer is, since this is a continuation, it expects the result of the parser. So the question becomes, what is the result of this parser? Well, we see that in the semantic function, we return another function that expects prop and returns comparison. And prop is a string. So our parser returns a function from a string to a comparison. And that's exactly how we define it. Next, how do we implement EQ? Well, first of all, EQ already parses, so to say, EQ because it's already defined as a method. Next, the body of EQ, which can be seen in the parsing function, calls the parser for prop and supplies it with a function that expects the result of the parser. That's what we do in Java code. We instantiate the parser and give it the expected function. Now, the remaining part is we want to apply continuation to the result of this parser. And what is the result of this parser? Well, let's look at the semantic function, which is called in the parsing function. And in our Java code, we will simply inline it. So we get the equivalent of our semantic function, which is from prop1 to comparison. And please note that even though this is a parser for the transform grammar, it calls the constructor for the original AST node. Therefore, it preserves semantics. Now, for completeness, here is the parser for prop, which is really simple, since prop has only the terminal prop in its body and it parses a string. It simply calls its continuation with a string. So, in summary, we started with a context-free grammar for EQL. We transformed it into LL1 to be able to generate a Fluent API and a parser. And then, when implementing our parser, we managed to reference the original abstract syntax tree, since we have modified our parsing functions and semantic functions accordingly. And with this, we can proceed to compile our DSL into whatever we want. This is the essence of this work. Future work entails supporting empty derivations in an elegant way, also supporting generic Fluent APIs, and of course coming to performance. And that's it. Thank you. Will there be any questions?
Okay, thank you very much. If you have a question, form a queue on the mic. So, and if I understand correctly, the ordinary compiler translate the context-free grammar to LL1 and convert back the generated AST to the original form. Is there any connection to that?
That is correct.
Yeah. Is there any connection with the normal compiler at the front end?
Sorry, is there any connection to normal compiler?
Yeah, if I understand correctly, the front end of the compiler does a similar process.
Which are you referring to a specific compiler or in general?
In general.
Well,
am I wrong?
I don't know about. Okay, so I'm not familiar with methods for compilation that take a context-free grammar, transform it into L1, and then are still able to build the original AST. So typically, they build a parse tree for the transformed grammar, which has this transformed shape and doesn't correspond to the original one.
Okay, thank you. And any questions? No? Then let's thank to the speaker again.
Okay, so